Perfect timing. Even the bell says so. Okay, so this is section 11.5 and 11.6. I think section 11.5 is just the intro to vectors. I think we've already covered that. And 11.6 are the problems. Maybe starts it. I can't remember. Okay, the whole point is, once again, we have position, we have velocity, and we have acceleration. But this time, we have it in 2 dimensions. So our position, we'll still call it S of t, but it is equal to a vector which has an x component with respect to time and a y component with respect to time. So is it parametric like? They say that I'm not supposed to teach them alike, but that's all the same math. So shh. But as far as I'm concerned, it's all the same stuff. Did you notice parametric, vector, and polar? It's all the same stuff. X is with respect to time, or X is with respect to theta. Y is with respect to time, Y is with respect to theta. It's the same thing. Okay, so we have position. And then there's velocity. V of t is equal to the derivative of x with respect to time and the derivative of y with respect to time. And so the other way to write it would be dx dt, dy dt, and that's a function that describes the velocity. And we have not just one dimension, we have 2-dimensional motion. And then there's acceleration. And there is no need to panic on this. This is really easy. Really, it is. Really straightforward. Don't panic if you don't take physics. It's okay, you don't need physics for this. This is just the math behind it. So we don't do all the funky weird stuff with it, we just learn the math. So x of t, double derivative, y double derivative with respect to time, which means second derivative of x with respect to time, and second derivative of y with respect to time. So do you just have to do derivatives? And then there's speed. And for our speed, it's the magnitude of the velocity, right? Well, let's look at it. We have a vector. Vectors have direction, right? And magnitude. Well, this is the magnitude. This is x of t. This is y of t. This is the velocity vector. That's the velocity vector. Well, that length right there is the magnitude, right? Do we agree? So all you have to think of is speed is just distance. But it's the derivative. I didn't do that right. There's tick marks there. This is, hang on. We got a velocity. This is velocity. So that's a derivative. So if we want this distance here, which is speed is that distance, it's equal to the square root of x prime of t, all of that squared, plus y prime of t, all that squared. And it is written as, I write with double straight lines because single straight lines look like absolute value, which is not really the same. It's sort of the same. By squaring it and then take the square root, you are getting a positive value, but it means a little bit different. So I write it as a different symbol. Okay, that's your speed. It's the magnitude of the velocity vector, which the velocity vector is written as x derivative is its x component, y derivative is its y component, right? And then there's distance. Remember how we learned that arc length formula? And we had to fiddle around with it to make it match? Remember that? And we ended up with square root of 1 plus the derivative dy dx, all that squared. Well, we don't have to fiddle around anymore. We have broken it apart. If I integrate speed over time, the square root right there, will that give me the distance? Think about it just a second. Distance is just the integral from a to b, whatever a to b is, of the square root of x prime of t, hang on, x prime of t squared plus y prime of t, that's a t, it's an ugly t, it's going to be a prettier t, squared dt. Really, really. You just got to remember speed is a specific, so it's the magnitude of the velocity vector, it's specific, and then distance is like how far I went at that amount of time. Yeah? Pretty straightforward, right? These are the easy questions on vectors, when they ask for speed and distance. That's the easy part. Well, along with if they give you position and ask you for velocity and acceleration equations. Okay, so here we go. So this is our first example. Example 1. Find velocity at time 1 and acceleration at time 2 given the following. And you are given that x sub t is equal to t cubed minus, no, plus 4t squared, and your y of t, so your y component, is equal to t to the 4th minus t cubed. And after you find, so that's part A, is find the velocity and acceleration. Part B is going to be find the particle speed. At time equal 1. And don't worry about units, I didn't make them up, but I should have. Okay, they gave me position. Can I easily find the velocity? The equation describing the velocity is going to be, what's the derivative of the x component? You can say it louder. 3t squared what? 8t. And what's the y component? 4t cubed minus 3t squared.
That was easy.
Right? If I want to know the velocity at time 1, do I just plug it in? 3 plus 8 is 11. 4 minus 3 is 1. Is that the vector describing the velocity at time 1? Yeah. Now let's find the acceleration. Do we just have to take the derivative of the velocity? What's the derivative of 3t squared plus 8t? 6t plus 8. What's the derivative of 4t cubed minus 3t squared? And if I want the acceleration at 2, I plug in 2. So 2 times 6 is 12 plus 8 is 20. 2 squared is 4. 4 times 12 is 48. 48 minus 12 is 36.
Einfach easy.
Yeah? Now, so we found the acceleration at time 2, and we found the velocity at time 1, and now they want us to find the speed. So this is part B. If I want speed, what do I need? The derivative, right? Is it the square root of, well, go back up here to velocity. What was my x derivative? Yeah? But even better, do I already know what the x component and the y component are at time 1? So I don't even have to, I just can take the values, because I already evaluated velocity at time 1. Can I just use those components and square them? I don't have to go back to anything. If I hadn't already done this, would I take this and would I square it and plug it in? By the way, you would not actually distribute, you would actually plug in the 1 and evaluate, right? Please say you would. Okay. So, is it going to be 11 squared plus 1 squared is the square root of 121 plus 1 is just the square root of 122? And we're not going to worry about it. Yeah? That wasn't bad. That was pretty easy, right? Very straightforward. The questions they ask you. Okay, let's do another example. In my next example, ooh, it's a distance one. This is fun. Here we go. So, in example 2, I'm going to be, so you are given the x and y equations. You're given x of t is equal to the square root of 3 minus 4 cosine of t in meters. And then y of t is equal to 1 minus 2 sine of t in meters. And you're given this is defined 0, your t is defined between 0 and 2 pi. And I guess we're going to call this seconds. Okay. And I'm going to give you the information that the curve intersects, oops, the x-axis twice. In the interval. Write an expression that represents the distance traveled by the particle between the two intercepts. Okay, what does it mean when it crosses the x-axis? What's the y value? 0, right? So they're telling you the y value at 2 times. So you just, to get the time intervals, do you just set y equal to 0 and solve? So we're going to have 0 is equal to 1 minus 2 sine of t. That means that 1 equals 2 sine of t. So sine of t equals 1/2. So you're going to tell me everywhere sine is a half between 0 and 2 pi. Where is sine a half between 0 and 2 pi? What times? First quadrant. What is sine? When is sine at a half? Pi over 6. Okay. The next place, the y coordinate, doesn't have to be in the second quadrant. What's the pi over 6 version in the second quadrant? 5 pi over 6. Everything else is negative. I don't want a negative half. I want a positive half. I'm going to keep it positive. Yes? Can I go to the next page? So, adding a page, our distance, and you can use that same symbol S if you want, is equal, and what am I integrating from and to? From the pi over 6 from the pi over 6 to the 5 pi over 6, right? And it is the square root of, what was my x derivative? So I need to get the x derivative, right? Plus my y derivative. And all I've done is the algebra so far. dt. Well, let's go find them. So what is the derivative? My x was square root of 3 minus 4 cosine of t. Okay, sorry. Go back and look at what x was. What's its derivative? When you're taking the derivative of square root of 3 minus 4 cosine of t, what's its derivative? Just sine of t, right? 4 sine of t? Sorry, I mean 4 sine of t, yes? Squared. Plus, what's the derivative of the y component? Cosine of t. Negative 2 cosine of t squared dt. And this is not fun to integrate by hand, but you would have a calculator. This is more than likely, these questions more than likely, because they're going to have to be a really contrived question if you don't. It's going to be on the calculator section. And you would put in the calculator now that you have this. Yeah? What? Not underneath the square root, it's not. It is, but you're going to have to, I would have to beat on it. I don't feel like doing it right now. No. You can't cross out anything.
It equals 1.
No, it doesn't. Because you have 16 of the sine squared and you have 4 of the cosine squared. You have a bit of a problem. Oh, yeah. Yeah, it's painful. Okay, but it's okay. You got a calculator for that kind of problem. Then we have another kind of problem. Example 3. What if instead I give you the position vector, and I give you that is 2t cubed minus 15t squared plus 36t plus 5. Oops, I didn't leave enough room. Oh, I did. T cubed, the y component is t cubed minus 3t squared plus 1, and it's meters. I was in a metric mood that day. I'm just making up units. And my time is greater than or equal to 0 seconds. The question is, for A, when is the particle at rest? Can we bring back all the questions I've ever asked for one-dimensional motion, and you can do it in two-dimensional with vectors? Okay, when is the particle at rest? It is at rest when what is 0? No, yeah, well, okay, which is velocity, right? So your velocity has to equal 0, 0. You're trying to find that time. Well, that's the derivative of x and the derivative of y, right? So I need to find those. See, this is x prime of t, and this is y prime of t. So I need to find when those are 0. So let's find x prime of t. Take the derivative of that beast. It's a polynomial. What do you get? I'm ready for y'all to catch up to me. I'm just writing it down. What is it? And then that? Yeah. Okay. When's the y equal to, or sorry, the y equals 0? What's the y derivative? What's the derivative of t cubed? Are y'all awake? Are y'all here? Am I by myself? I'm feeling very lonely. Okay, after that, do you just do algebra? So I'm going to factor out of 6. I get t squared minus 5t plus 6, which is easy to factor. Would y'all factor it correctly? Oh my, y'all will just make me crazier than crazy. Because It's not 6 and 1. It's 2 and 3. Because that's a minus and that's a plus. For this one, it's easy. We just factor out a 3t and left with a t minus 2. I made a boo-boo. It's a minus 6t right there. I was a dit, sorry. I was gonna say I think I wrote it correct there, and I did write it correct there. I was going too fast. Okay, so what are the times when the x component is 0, 2, and 3? When is the y equal to 0? T equals 2. So where's the only place that's actually at rest? 2. What do they have in common? This is the tricky part. Y'all can do all the math, and then y'all don't know that it's when time equals 2, right? Does everybody understand what I'm saying? So the particle is at rest at time equal 2. And you would write the particle is at rest at t equals 2 seconds. That was easy. Yes? Okay, let's do another kind of problem. There's another kind of problem. I got one more. This is my last problem. It won't take long. Example 4. I might go to a new page. That might help. Example 4. And then y'all are on your own. Example 4. We have velocity is equal to 3t squared minus 4t and at squared plus 5. And I'm going to tell you that there's some initial position. Does this look familiar? Only you've only done it in one dimension. My initial position is an x of 7 and my y is negative 4. And I want you to find the position at time equal 1. So find position at time equal 1. We're going to say minutes this time. And this is feet per minute. And this is feet. I'm just making it up as I go along. I guess whatever. Okay, is this that net change future value? Oh, somebody taught you that to make this easy. So is my x component at time 1 equal to my initial position? What was my initial position for x? 7 plus the integral from 0 to 1 of the x derivative, which is 3t squared minus 4t dt. And what's my y at 1 going to be? My y component, which is negative 4, plus the integral from 0 to 1 of the y component's derivative, which is 8t squared plus 5 dt. And is that easy to integrate? So for my x of 1 is equal to 7 plus the antiderivative for that, which is t cubed divided by 3, so it's going to be t cubed plus, sorry, not plus, minus, and 4t, that's squared over 2, so it's 2t squared. Evaluating from 0 to 1. Notice I wrote the integral, trying to make an S, squiggly S, right? And it's a straight bar at the back side, because I don't want to get these two confused. Y'all don't want to confuse me, do you? Doesn't go well for your test grade. 1 minus 2 when I evaluate it, putting in, and then there's minus 0. What does that equal? The x position is 6. The y is going to be the negative 4 plus, I got to integrate from, I already did the integral. Wait, it's right there. So it's going to be the antiderivative of 8t squared is 8/3 t cubed plus 5t evaluated from 0 to 1. That's easy math, right? Did I lose my mind? Yeah, no, wait, that was already cubed. This is supposed to be cubed. It doesn't work out too very pretty when you write squared. It's cubed. I want the math to be nice. I didn't want to make an ugly problem. I don't want ugly fractions. Yeah, 8 over 4 to the 4th. Much better. Much, 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 much better. Much more better. Okay, so when I plug it in, I'm going to get -4 plus 2 plus 5 minus 0. So my position at time 1 is equal to 6, 3.
Muito mais fácil.
And we're done today.